Hello, everyone. I'm Daniel Smith. I'm a software engineer at Google. I was one of the first individuals on the Kubernetes team back before we open sourced it, before we released it. So this talk is something that I did at Google. Actually, it was two parts. I did it for new team members. If you've ever been through the Google new employee orientation, they've got a series of classes, lifetime of a server, lifetime of a query, all these things. So I thought it would be good for new team members just to see a lifetime of a Kubernetes API request. And apparently all of you agree. I thought there'd be like 5 people interested in this. So the question that we're going to try and answer here is, what happens under the hood when you start up a kubectl command? Specifically, I picked replica sets because they're relatively simple. So what happens when you type kubectl create -f and some replica set .yaml? And it turns out there's actually quite a lot that happens. So I had to cut out some stuff to fit this into the time. So I'm sure I cut out your favorite part. Sorry. So these are the things that we're going to go through. Is what happens inside the kubectl binary. Then we're going to have a short interlude on what happens on the wire, conversion, serialization, defaulting. Then we're going to go through what happens once API server receives a query. And then last, we're going to go through what does API server do after it's received a query. So those are the 4 things that hopefully we'll get through. So this talk is sort of aimed at people who are interested in the Kubernetes code base. So I'm going to actually have code on my slides. I don't expect you to read the slides as they're up there. I'll try and point out relevant things. The slides and the recordings, the feedback I got from the talks I did inside Google is that people like to watch this and sort of go look at the code, pause it occasionally and go browse through the code. So I have included on these slides all the function names are links. You can click there, it'll take you to the 1.4.5 version of Kubernetes, and you can just sort of use this as your guide to the stack. So treat this as reference material. The code, to fit anything meaningful on the slides, I had to basically delete mostly everything. So take everything you see in the slides with a grain of salt. Click on the link before you trust anything. So with all that said, let's dive in. So the first thing that happens when you run kubectl is that it builds all of its available commands. This happens every time you start it up. We use the Cobra library. The output of this process is documentation and also commands that can be executed. So I have here on the screen the setup code that creates the create command. Not too special. You'll see down at the bottom the run create function call. I don't know if you can read the slide or not, but the run create function call is what does all the work, which I have on the next slide. So if you could read the slide, I think it's a little fuzzy, but if you could read it, you would see that it invokes something called a factory. It makes a builder and it makes a helper. What are these things? These are the 3 components of kubectl. If you do anything involving a kubectl command, you're probably going to interact with these. So I'm going to run through what each of them is. First up is the factory, and this is like replaceable logic for kubectl. I know OpenShift overrides it in OpenShift's command line client. So it's basically just drop-in things. Like one of the function gives you a client that talks to a Kubernetes server. The one that we'll look into further is the unstructured object, which gives you just a mapping between an object type and a REST path on the server. This is used to do generic generic REST operations, which is what we're going to show in a minute here. So this is the factory, and there is a function linked here which builds the factory. It's like 600 lines of code. I counted. It's just full of like function definitions, and again, OpenShift overrides this. This is drop-in logic for kubectl. Yeah. So next up on our list is the builder, and I didn't name these things in kubectl. And by the way, this talk is more of a history lesson than it is like this is the way I think things should be. We started off with a lot of little bits of code, and over time they grew layers, and the layers grew layers. Kubectl isn't that bad. This builder thing is actually necessary. The task that it performs is all your when you invoke kubectl, you have like a -f command, or you can pipe in standard in, or you can give it a directory, or you can give it a file with a bunch of resources in. The builder is responsible for unpacking that and turning it into a list of resources to iterate over. Yeah, so you can go browse the code if that interests you. And finally, the last part of kubectl that we're going to look at is the helper, and this is responsible for like generically taking some resource and doing some REST thing to it. So in our case, it's taking a replica set and it's calling the create method. You can see at the bottom here, I don't know if you can see. If you could see, at the bottom there, it has a chain of commands like post, namespace, resource, body, do, get. That's interacting with the next layer down, which I think is on the next slide. Yes. The next layer down, so now at this point we've exited kubectl. We're in the Kubernetes client library, which is now published separately, and you can use this code in your own projects. And in fact, the links on this slide go to the client Go library and not the main Kubernetes repo. You can see the REST client here is basically just a helper tool that helps you build a resource path, a URL that refers to a Kubernetes resource. It's got a series of helper functions. So you give it a verb, you can give it a prefix, a suffix, a resource, like replica sets in our case, a sub-resource, the name of your object if you're doing like a get, a namespace. Yeah, so this is how you build up a request. One thing I wanted to hit on in particular is the body method. I think it's kind of nice. It lets you pass in the body in multiple formats. So you can pass a string directly, you can pass an array of bytes, you can pass a io.reader, which is probably what you want to do if you're following ordinary Go conventions. Or you can pass in a runtime object, and runtime object is really the type that we've made in the Kubernetes code base to represent Kubernetes API objects. Yeah, so it sort of does the right thing. One thing to look is this runtime.encode there. I don't know if you can see. That is calling down into the serialization machinery. So that is the place where the magic happens of taking some object that you have in memory and turning it into bytes that you send over the wire. Okay, we'll get to that in a second. Finally, once you've constructed a request, you call this do method. It actually goes out and executes an HTTP request. I didn't put this function on a slide, but if you're interested, you can go see the code where we actually make the Go HTTP client and execute a request. And then once it gets a response back, it transforms that, which might involve turning a blob of JSON into a Go error type and sending that up to the user. Okay, so that was the kubectl side of things, and we've gotten bytes out onto the wire at this point. And so I thought it might be good to talk about we've got if you've looked at our code base, you know that there's a bunch of automatically generated code that does a bunch of strange things. And I don't think we have time to go through all of the things that this code does, but I wanted to sort of tell you what the problems are that this code is solving and why do we have this complicated machinery. So the basic problem for serialization is we have some memory structure. We have to have some canonical way to put it on the wire. Otherwise, we can't share it with anybody. For conversion, why do we have conversion? We have old clients, and Kubernetes is infrastructure. People write important clients against it. People write important clients that work with, two or three or four older versions of Kubernetes, and we want those clients to continue working. Otherwise, people are not going to be able to upgrade. So that's why we have some conversion machinery. I'm going to talk more about these in the next slides. And lastly, why defaulting? The reason why it's here is because we implemented it in the same way that we implemented the other two. But the basic problem is there are fields in our API objects which have default values, and sometimes these fields have some small number of values that are actually acceptable, and old clients don't know what those fields are. So somebody has to default them. So serialization. In Kubernetes, we serialize to JSON primarily, and Clayton and some other of our friends at Red Hat have written a proto serializer. This is not the standard proto serializer. We needed to maintain compatibility with our code base. So it's actually really impressive. He's got a thing that generates a proto message from the Go structs. It's pretty cool. It's more generated code though. For JSON, we use a tool called Ugorji, which generates decoders for us. Although Tim was just telling me earlier today that he's working on writing a replacement. Ugorji runs really slowly. I don't know if you've ever rerun our generated code. It takes a while. So I thought I would show you not the machinery itself, but just some of the interfaces that we require objects to conform to. This is the runtime object interface. So all of our API objects implement this interface. A little bit of trivia: for the longest time, this interface had one function which was called is a runtime object. It didn't do anything. It was just there to let you mark certain structs as runtime objects and let the machinery operate on them. Eventually, we changed this to get object kind, which performs a more useful function and replaces a bunch of machinery that use the reflect package, Go's reflect package. So this is much faster. We have, because we support both JSON and Proto, we have to have an interface around our encoding and decoding machinery, because you could have a blob that is Proto or JSON. You need your code to work with both. So this, here I've shown the encoder interface, the decoder interface, and the serializer interface, which is just the two of them together. Let's see, I forgot what I was going to say. Yeah, so you have a blob, you don't know if it is Proto or JSON. We have an interface to manufacture a serializer for you. Oh, I remember what I was going to say. I'll say it on the next slide. So the negotiated serializer interface will give you back a serializer for a particular media type. So this goes a little bit beyond just Proto versus JSON. It's also, it also deals with encoding, so content type header, that sort of thing. We're going to add more in the future where clients will be able to set the accept header and get back results in a format that's more to their liking. So this is the mechanism that we'll be using. And at the bottom of this, you see encoder to version and decoder to version. That is where the conversion machinery comes in. So like I said, the goal of the conversion machinery is clients speak old versions. We want to keep those clients working. This is really kind of why we ended up with a weird conversion machinery, a weird API machinery. Like if we did this again, would we do the same thing? I don't know. Maybe. gRPC did not exist when we started this, so that wasn't an option. We haven't switched to gRPC for a number of reasons. One is we have existing clients that expect this now, and we can't break them. Yeah, it's complicated. So what I was going to say is that Proto itself does not have a great system for keeping old clients working. There are some rules you can follow to keep your Proto messages compatible, backwards compatible, but it works best in a situation where you're like continuously rolling out a service. It doesn't work great when you have clients that can be an arbitrarily far number of versions behind you. Yeah, especially if you want those clients to continue to work as opposed to like just not crash. So we came up with this machinery. It works. It's not pretty. Yeah. So our solution basically is we'll just keep the older versions in tree, and we write. We actually automatically generate some functions that convert between the old and the new format. In terms of what that looks like in code, it's actually exactly the same interface as the serializer. It just has different semantics. So the serializer is not going to manipulate the data in any way. It's just going to take it from wire format to memory format. The codec may additionally transform the data in some way by turning it from, like, if it's V1 on the wire, maybe it'll be V2 in memory. Or we have this concept of an internal version, which is like the hub of the conversion diagram. So all versions can be turned into the internal version, and the logic in the server can be written understanding only the internal version. Finally, defaulting. Like I said, clients may not understand new API fields. The solution is the server adds default values for fields. Until recently, actually, kubectl was unfortunately adding default values using the same machinery because it's built into both the server and kubectl. But we've taken it out of, I think, create and update at least, and we'd like to take it out of more places in kubectl, because really you want the server to be applying the defaults, because the server has the best idea of what the defaults should be. Little trivia about the defaulting is that it is applied recursively, and so currently fields are defaulted multiple times. This is a bug. Unless somebody's fixed it. I've been out for a few weeks on paternity leave. Hopefully somebody's fixed it. Okay, so enough about conversion. Let's run through API server's processing of requests. So I've started here with the run function in our generic API server library. We're making efforts to separate out non-Kubernetes specific things into this generic API server library and keep the Kubernetes specific things in just the plain old API server package. There's a number of reasons for this, which I won't go into. But basically, we want to make it easy for people to build Kubernetes-like APIs. And we don't expect you to write this from scratch. We'd like to, there's a bunch of stuff that can be reused. So this is the run method, and the slide is indistinct, but at the top it adds some, what does it add? It adds some rate limiting. There's a timeout handler. It adds a rate limiter timeout enforcer to the request. And then here at the bottom, it actually calls listen and serve TLS. So this is sort of the entry point for the socket where it starts listening and serving. Let's see. So then this code is all happening at setup time, like when you start the API server binary. This function is initializing the handler stack. So when requests come into API server, something accepts the request. It goes through this stack of the Go HTTP handler interfaces. It goes through the stack of them, and each one like checks something and then passes it along to the next layer. So as you can see, like the list, the bulleted list is actually the opposite order of the order they appear in code. This is because each handler wraps the previous handler, so they actually get invoked in the opposite order that they're added. I think there's actually a bug on this slide. I think we're calling authentication and cores in the wrong order, yeah. So after it gets through, so the handlers are a timeout. It adds a context. It goes through authentication. It checks cores, and it adds the logging handler, and then finally it goes through a series of dispatch operations. First, it goes through the muxer that the Go HTTP library gives us, and then unless it's one of there's only a few URLs that handles, and then it is otherwise passed through the muxer that we set up with Go RESTful. So how do we set up the muxer that Go RESTful uses? I'm glad you asked. This is the API group version struct. Our API is divided up by group. It's divided up in other ways, but the important thing for setup is that it's divided by group. So each group has one of these structs filled out for it, and then we pass it along to the API installer. So you can see that we put in a bunch of helper things. So there's a negotiated serializer that's passed in there. So before creating this, you have to set up a serializer that can understand all the various formats that you want this to use. And there's also a storage. Way back in the day, it was called storage because it was actually storage. It's grown a few layers since then, and now this is actually the thing that handles the REST request, the business logic, which it wraps an actual thing that is really represents the storage, which we'll get to in a few slides. But yeah, so it has all this. It has an object typer, a creator, a converter, linker, and a bunch of other things. So that all gets tossed into the API installer, which starts off innocently looking. It's got this install function, and it just runs through all the groups, and it calls some Swagger and Open API setup code so that we get nice API documentation as it's building the paths. And then it calls this register resource handlers function. And unfortunately, if you drill into that function, you'll find that it is very, very, very long and not easy to follow. But basically, it sets up a long list of handler paths that it then programs into Go RESTful. And I've excerpted onto this slide only the create one. But just imagine this code copied and pasted like 18 times for all the different handlers. There's a big switch inside this for loop. Yeah. But that I don't know if you've ever used Go RESTful before, but that is programming Go RESTful. It tells it what verb it is. It tells it where to route it to, this handler, which it gets from this create resource function. It gives it a documentation. It lists some parameters, and then it finally installs it. Yeah, so that's how we program Go RESTful. Okay, so finally we're getting to something that is happening not at initialization time, but actually at runtime when a request is received. If you look at this create handler, this internal function, you can see it's actually doing a bunch of interesting things. It does version and format negotiation. It calls that serializer. It reads the body. It does the decoding and the conversion to a specific version. Then finally, it calls into I called it a registry. It's the storage thing, the business logic. After that is done, it sets a self link on the result, and it sends it back to the user. So let's go down a layer into the next set of layers, which is the storage interface. And originally it was one interface, but it's grown into an interface per operation, basically. So I'm only showing you the creator interface. So basically, when you define your object, you can define like just a create method of like this signature, and if you send it through the API installer machinery, you will support the post verb. And we have a bunch of different interfaces, one for each verb and some for various sub-resources. Yeah. So since that's a lot of work to implement, we have a implementation ready-made for you. So all you have to do is supply something that implements this strategy, and most of the work is done for you. And just to show you how, well, okay, so this is the work that is done for you. This is the create function. So when you create anything, it runs through this code. At the top, it calls before create. It does some stuff for you that's the same for all objects. It calls create. And finally, it does after create. Makes sense. So when you go to implement a strategy, and this is the replica set strategy, you actually don't have to write too much code. So here it is setting the generation to 1. We could be here for another hour-long session to explain the generation, so we will gloss over that. I also showed the validate function. Okay. So what we just saw was sort of the user-facing half of the API server stack. Now we're going to show the storage-facing half. Because API server, those are the two main things that API server talks to, is users and storage. So we have to store things. So this is the interface that all of our business logic expects from a store. So this is, and I didn't show it all. This has got create, delete, watch, get, list. I think there's a update or a set. Yeah, so this is the interface. We have in the code base etcd2 and etcd3 implementations. I'm showing links here to the etcd3 implementation, but the etcd2 one is right next to it, so it's easy to find. This is kind of critical code. Like, you don't want to write something to Kubernetes and have it vanish off into the ether. And the other reason why it's critical is if you're watching, it's really kind of important that if you list and you pass the resource version back and you initiate a watch, that you don't miss any updates. So this really needs to be tested very well, which is why I say on this slide we are open to interfaces or implementations for more storage backends. But there's a high bar in terms of testing, continuous testing, scale testing that needs to happen here, which makes it difficult. So I just thought I would throw that out there. Just for fun, this is the etcd3 implementation of create. I actually don't understand the etcd3 code, so the part that I wanted to point out is just it's using an embedded codec. It's called runtime.encode. This is calling into the conversion machinery that I was talking about earlier. And this is because when you start up a API server, you get to tell the system what version to write to its storage. And this lets you control like when you do storage format upgrades. So we actually understand multiple versions, but we write out only in the specified version. This lets you do roll forward or roll back between versions. So good to know. Okay, so how do we get that codec into the storage pointer? We have written a factory to help you do that. This code is in the generic API server, and it actually works off of command line options that you pass to API server. So if you were to make your own API server, you would probably not need to mess with this. and the thing to know about the storage options that we take is that you can actually specify different resources go to different etcd clusters. So by default, events are stored in a separate etcd. Our default setup scripts store events in a separate etcd. Like you can customize it arbitrarily if you really wanted to. Like you could, I don't know, maybe make secrets go to a different etcd or something. I don't know. But that's something you need to be aware of if you're messing with this code. Okay, finally, I wanted to show sort of the glue that calls all of these constructors and factories and wires it all up. So this is also called install APIs, but it's on the master object and not the API installer. And this is where the master package collects all of the different resources and sets up that group resource struct that I showed earlier. Yeah, so this is where it assembles a storage and the codecs and all that stuff. And finally, I wanted to show like the specific code that sets up the replica set object is here and continues here. So this is where the business logic is constructed, basically. Yeah, so you can see here the customization of the various different parts of the strategy. And I think that is it. This was somewhat abbreviated from the talk I gave at Google, so hopefully this was interesting and useful. If you think that there's one or two too many layers in this stack, I would love for you to show up in the API Machinery SIG and help me make it better. Thank you. Any questions?
What are the slides you mentioned, like self-link or something?
Yeah, the self-linker?
Yeah.
Yeah, all of our API objects have a metadata section. One of the pieces of that metadata is the self-link, which instructs the user, like, if you just get the blob of data, how do you go find where it came from? The self-link tells you that. And so it's part of the machinery to fill in the self-link. Otherwise, everybody who implements their own resource would have to do that. And if you've been around programmers for more than 5 minutes, you know that if you make them do the same thing twice, there will be bugs in at least one of those things.
The changes in 1.5, generate APIs, what happened to changes?
What are the changes in 1.5? Funny you should ask. I've actually been out on paternity leave for the last 3 weeks or so I'm not entirely sure what's making it into 1.5. This is my first day back. I know we were planning on various improvements. I don't know off the top of my head what actually made it.
Yeah, my understanding is this machinery is going to improve.
Yes, it's definitely going to improve more.
1.5 is a lot of changes.
Yeah, in particular, I know Clayton had a bunch of changes planned to support more formats in the negotiation. So like the stuff that you do when you do kubectl get, the formatting, we were planning on moving that server side. So we'd like the server to implement that for you. So that would be an additional like content type.
One thing that I found very challenging is that I wanted to write an application that actually reads an object that's supposed to be Kubernetes object. And my question is, is there any plan of actually supporting those encoders and decoders as like a separate library that I can call in my application to use them?
Yeah, so the question is there any plan to move encoders and decoders into a separate library so that they're easier to reuse? So we have moved the client into a separate library. I think the plan is to move more things. Like we would like the API machinery to basically grow into a few libraries. So Yes, I would say that that's definitely in the future.
So the right approach is to use the client instead of the encoders and decoders directly, right?
Yeah. So right now I would definitely recommend that you use the client library that we published, and that actually includes a fair amount of the encoders and decoders. But I think we're going to want to move the encoders and decoders into yet another library that can be consumed by both the server and client side. Actually, we would like the conversion part of that to be only linked into the server component, because we want the clients to be simpler. And because the server is taking on this effort of converting between versions, the clients really don't need to, with the single exception of kubectl convert. And we want to move that functionality into the server anyway. Because if you imagine a world where you have multiple API servers, not necessarily all Kubernetes, you can't really reasonably expect every single API resource type to be compiled into kubectl. So we want kubectl to be able to call out to the server to get that done.
So different resources going to different etcd cluster, is that something configurable through the manifest or just code?
That is configurable through, the question was the different, having different resources go to different etcd clusters. How is that configured? That is configured through runtime flags that you pass to API server. So I can't promise that they're super well documented, but if you dig around in there, you should be able to find them.
Can API server take multiple etcd clusters as an argument?
Yes, you can actually pass lists into it. I forget what the exact format is. The help on the relevant flag should tell you, but it's something like a resource type equals and then comma separated. Yeah. Arguably, that's more than you should be packing into flags, but that's what we do.
Does API Machinery handle registration of new resource types?
Does API Machinery handle registration of new resource types? Yeah, I want to say yes. Like, it's our goal for that to be easy, and we have another goal, which is you should be able to implement a resource type in your own API server, and we should be able to combine those at runtime. Because right now, basically, you have to get stuff compiled into core if you want to test it out. But we would like to get to a world, like you have third-party resource right now, which gets you some functionality, but we would like to get you a little bit more functionality and let you reuse our components. There's a design out there for there's a design in draft code for a discovery summarizer that'll actually merge multiple API servers and present that as a single thing to a client. So, yeah.
It's probably better thought as an issue, but I just came to my mind. I run kubectl proxy in a container as a query API, and there's certain, I guess you would call them groups, there's certain groups, I think the data, some of the data resource types that I'm not able to get via that method, but I can get them.
Okay, so
not running it as a proxy in a container.
So the question is running kubectl proxy in a container. The beta API groups don't seem to make it through.
Yeah.
I can think of several things to check. I know kubectl proxy has some. There's some filters on it that control what exactly it allows through. So you might look at those flags to see if those are blocking it. If that doesn't fix it, I'm not sure. File an issue. Yeah.
So can you say anything about the authentication of these APIs? How does that work?
Yeah, I did not cover the authentication stack in these slides. I think that could be another talk, even longer than this one. Yeah, we'd have to get David Eads or Jordan Liggett to do that one. Anything else?
Some of these APIs are noted as beta and extensions. And should we be using them, or what is the point of deployment?
Should we use APIs that are marked as beta? Beta means that We promise it won't blow up the rest of your cluster if you turn it on, and it means that if you start using it, we are going to take on the work of keeping you compatible. So we'll make it easy for you to upgrade. So it's sort of up to you if that is acceptable or not. I can say for GKE, Google's hosted Kubernetes, we turn beta things on by default. So yeah.
You talked about the generic API server and basically separating it from the Kubernetes. I mean, it's not Kubernetes specific, you said. So, is there a goal like you wanted to use it somewhere else?
Yeah. So the question is generic API server. It's not Kubernetes specific. Do we want to use it somewhere else? We have a few use cases in mind. We would like OpenShift to be able to import generic API server directly instead of forking. Heapster, which is a component of Kubernetes, which does monitoring stuff, we would like them to be able to import it directly. I think that actually is working. Okay. Once we get those two target use cases sorted out, basically the idea is anyone who wants to prototype or even launch a in-house Kubernetes API could use that and use the federation machinery that I mentioned to like merge it with the base cluster. Yeah, so we want a way for people to launch their own custom APIs on top of a Kubernetes cluster. We don't want you to have to modify the kube API server binary that we ship.
You briefly entertained the question of what would you have done different if redoing all of this. Is there anything off the top of your head that is an obvious yes, we do it a different way?
I'm not sure. The question is there any obvious thing that we would do differently? I'm guessing that if we started the project now, given that gRPC is out there, even though it doesn't support sort of the conversion case that we really wanted to support, I'm guessing we might end up using it, but that's a total guess. A total guess. Yeah. Yeah. I mean, a lot of what we do is like we are at point A, we need to get to point B. The market needs this thing built yesterday. We are incurring technical debt as we get there.
So since etcd version 3 supports gRPC, are the APIs talking in gRPC to etcd3?
Yeah, so the question is, etcd3 supports gRPC. How do we talk to etcd3? Over gRPC, yeah. There's a bunch of benefits for this. We're going to start actually storing. Depending on how much progress was made while I was on paternity leave, the goal was actually to start storing objects in proto format for 1.5. We need etcd3 to do that, because otherwise etcd2, we have to talk JSON to it, which means encoding proto basics to forwarding it. That's very wasteful. So that's why we want to get to etcd3. It's one of the reasons.
Actually, I have a follow-up on that. Does that mean we'll be able to store binary config map data?
The question is binary config map data. At least 3 weeks ago, I recall seeing a PR to actually add binary, like a config map has a map of string to string, like to add a map string to byte array. Yeah.
The other question was, you mentioned that protobuf was not good for clients that may be many versions behind. Would you recommend it against it for like native apps that might not get updated for a long time for that reason? Does Google not use protobuf for?
Google definitely uses proto everywhere. Yeah, I don't know if I'd make a recommendation without knowing a lot more detail. All right. Thanks everybody.